Welcome to the Explainer. I am so incredibly excited to have you here today because, well, we are going to demystify some of the most fascinating yet consistently misunderstood concepts in all of software design. If you've ever felt completely overwhelmed by complex architecture or, if you just love discovering elegant ways to structure your systems, you are exactly in the right place. We're going to break this all down visually so it makes perfect sense. Let's get right into it.
So, what happens when writing quote-unquote good code actually makes your life harder? It's a total paradox, right? I mean, we're taught all of these foundational best practices, but sometimes following them to the letter can create massive, unexpected headaches. If you've ever found yourself drowning in a sea of perfectly structured yet totally unmanageable code, trust me, your struggles are perfectly valid. Today we're going to unpack exactly why that happens, and more importantly, how to solve it.
Okay, let's dive into this. Here's our roadmap for the Explainer. First, the decoupling dilemma. Second, the nightmare of complex wiring. Third, enter the facade pattern. Fourth, the official definition. And finally, number 5, the Law of Demeter. All right, moving right along to Section 1, the decoupling dilemma. To really understand the brilliant solution we're going to cover today, we first need to understand how we get into trouble in the first place, which, ironically, starts with the very best of intentions, specifically when we try to follow the single responsibility principle. Now, in object-oriented programming, building highly decoupled systems is generally considered a fantastic thing. This means having lots of distinct classes where each does one small thing perfectly. You keep following the rule that each class should only have one responsibility, and naturally, you end up with a lot of different highly specific classes. But as we're about to see, this architectural purity, it comes with a hidden cost that completely sneaks up on you.
To illustrate this hidden cost, let's look at a classic example from the famous Gang of 4 Design Patterns book. Imagine you're building a compiler subsystem. It makes total sense to structure your program into distinct classes, right? A scanner, a parser, a token, a symbol. You have this really high level of abstraction, and each piece handles its own specific job perfectly. It looks incredibly neat and tidy on paper, doesn't it?
Well, that brings us to Section 2, the nightmare of complex wiring.
Here's where things get messy. We're moving from the pristine mathematical theory of perfectly decoupled classes right into the harsh, messy reality of actually trying to use them together to do something meaningful in the real world. Just look at the ridiculous gymnastics required here. Let's say you want to instantiate class A, but it needs class B. So you say, okay, new B. But wait, B actually requires C, so you make a new C. But actually, no, that doesn't work either because C needs a reference back to B to function properly. So the process becomes create C with no arguments, create B, set C inside B, then manually set B inside C to fix the circular references, and then finally pass B to A. It's complete madness. You are doing all this non-trivial, complicated wiring just to get a basic data structure set up to do useful work. The decoupled system is great because it's composable, sure, but the setup has become an absolute nightmare.
Thankfully, there is a better way. Section 3, enter the facade pattern. If we have to do all this complex wiring just to make our beautiful decoupled classes work, we desperately need an easy, reliable way of doing it. Basically, we need a specific pattern designed to hide the chaos. And a perfect metaphor for this is a house. Think about the plumbing, the insulation, the foundation, the wiring, basically all the chaotic mandatory subsystems required to make a building function. You absolutely need them to construct a building, but you don't want to be staring at exposed pipes and wires all day in your living room. So instead, we put up a facade, a clean, elegant exterior face. It's a unified wrapper that makes the house an absolute joy to interact with.
Bringing this back to code, the facade simplifies interaction by wrapping the complex subsystem wiring into one unified class. Your client code doesn't need to juggle class A, B, and C or worry about dependency injection and fixing those annoying circular references. Nope, it just talks to this one simple facade class. The facade handles invoking all the methods on the various underlying objects for you. The chaotic plumbing is still there, completely unchanged, it's just neatly hidden away behind a beautiful interface so you don't have to deal with it directly every single time.
So, let's lock this in. Section 4, the official definition.
Now that we grasp the concept visually, it really helps to anchor our metaphor into the formal academic text. Let's look at the exact phrasing from foundational materials like the Head First Design Patterns book. So the crucial point is this. The facade pattern provides a unified interface to a set of interfaces in a subsystem. The facade defines a higher-level interface that makes the subsystem easier to use. See how perfectly that textbook phrasing matches our house metaphor? It isn't adding new functionality to your underlying system at all, it just provides that higher-level interface, the clean face of the house, making the complex subsystem incredibly easy for the client code to interact with.
Let's move on and see how this builds into our next big concept. Section 5, the Law of Demeter. This principle seamlessly builds on our ongoing discussion about taming complex coupling in software. The Law of Demeter is also known as the principle of least knowledge, which honestly is a fantastic and descriptive name. It's an attempt to reduce coupling by strictly limiting what objects your class is allowed to know about and interact with. The foundational idea is pretty simple. Knowing less makes your code less likely to break when other things in the system inevitably change.
Let's look at a somewhat sloppy but highly intuitive interpretation of this rule. First, consider what is allowed, calling A.B. This is essentially like talking to your friend. But then consider what is strictly not allowed, calling A.B.C. This is like talking to a friend's friend. So why is that bad? Well, because if you bypass your friend B to talk directly to C, you are now highly coupled to the internal structure of B. If B changes how it works under the hood, your code suddenly breaks. You are entirely too dependent on strangers.
Now, while that A.B.C rule is a really helpful mental shortcut, the actual strict textbook rules are outlined right here as the 4 allowed invocations. If you are inside a method, you are only allowed to invoke methods on yourself, methods on parameters that were actively passed to you, methods on objects you instantiated yourself within that method, or finally methods on your own components, meaning your instance variables. I know, it might sound a bit strict at first, but adhering to this severely limits dangerous, brittle coupling across your entire system.
But look, if you remember just one thing about managing coupling from this entire explainer, let it be this brilliant, sticky catchphrase from the source material. Talk only to your immediate friends. Absolutely do not talk to the friends of your friends. Keeping your interactions strictly local ensures that when systems inevitably change, and they always do, your code remains robust, flexible, and completely shielded from the fallout.
Which leaves us with this final, somewhat provocative thought. Take a look at the code you are working on today. Are your classes getting a little too friendly with strangers, blatantly violating the Law of Demeter? Is your setup a total nightmare of complex wiring because you've created a highly decoupled system without providing a unified interface? If so, is it time to finally build a facade? Thank you so much for joining me on this explainer.